start this morning session with the last lecture of Leopoldo about CFT, ADS CFT correspondence. Please.
Okay, so more or less what we have done so far is in the first lecture, first two lectures were mostly about the general formalism of ADS CFT. Then yesterday I went into some more specific application. This essentially goes into the area that is roughly known as ADS condensed matter. Okay. So what I want to do today is to essentially, I'll go back to discuss a very core aspect of ADS CFT. So my plan today is to talk about Wilson loops. Okay, when I show you applications, I said I show you, one was the scalar field and how to get correlators, scalar correlators there. And then the other example was the Wilson loop, the rectangular Wilson loop. So today I want to, all the time I will spend on the circular Wilson loop. So this is a half BPS. I'm not getting into a lot of detail, but this is a very important operator. I already sung the praises of the Wilson loop in any gauge theory, but in particular in any N-4 super Young Mills, this is a supersymmetric operator. That means, as you probably know, that you can do that you can compute it almost exactly. In fact, you can compute it exactly. Okay, and what I want to do is to use this as a precision test, if you wish. So we have data which comes from field theory and is exact, and then we want to see how much that helps me understand the ADS CFT part. So what I plan to do concretely is, first I'm going to talk about perturbative, well, not only perturbative, but I'm going to basically evaluate the Wilson loop. Okay, this was going to be just field theory, just as a question in field theory. What I'm going to do first is the most obvious, which is perturbative. I'll show you some perturbative evaluation. There will be some kind of Feynman diagrams, but very simply. Then I want to introduce very, very briefly. I will introduce localization. This is a technique that will allow us to compute the Wilson loop exactly. Okay, it will define it exactly as a matrix integral, and then I will do that matrix integral for you. This is a technology that goes on the domain of matrix model. Okay, then I will go to the holographic part. So in holography, I want to compute, as I said, my goal is to do essentially what you do in quantum mechanics with the hydrogen atom, for example. So you compute first the levels, and then you said, okay, but this I could have gotten by accident, by thinking that an electron is like a small planet going around some other planet or something crazy like that, will still give me the right answer. So that essentially happens a little bit in the ADS CFT. I get the leading term, so I want to talk about the leading part, which will be just a classical calculation, as we already did. That will match nicely, but I'm interested in subleading, so really like the more quantum aspect. So this is roughly the goal of this last lecture. I want to present this area as an area where we can test the more quantum aspects of ADS CFT. We go beyond the leading approximation, where many things are supposed to work just by seeing. So that's the plan for today. Again, if there's extra time, I will give you some bird's eye view of where this field is, what are the really big puzzles that people are trying to figure out, and some of my own work. But that's again, if we have time. Like if you, I'm going to write one in, because it's going to be just a very impressionistic view of what's going on. But again, this is the goal. My goal, okay, this is a school, so a lot of this I could have just stated, okay. But I want to flash for you some of the important techniques that you would need to learn if you want to work in this field. And it's a very beautiful area with a convergence of many interesting ideas, again, in field theory and also in gravity. But I think this is going to be I'm discussing a very specific object, but I want you to view it as a lesson of all the different techniques that enter to answer this question. Okay? Good. So you've already heard a lot about the Wilson loop. So now let's do a field theory calculation. Okay. So what is the object that I'm interested in? So the Wilson loop depends on the contour. My contour is always going to be a circle. Okay, but the definition, let's talk about in the fundamental representation. So this is the trace, path ordered exponential of I, a mu, it depends on x dot mu. Okay, so let me write. So I could have written d mu here, but I'm going to, you see I wrote that. So this is a curve that is parameterized, sorry. This is parameterized by this parameter tau. Tau is the parameter of my curve. Then dx mu will essentially be x dot mu. And this. So this is, of course, this is just the natural thing that exists in any field theory. But in N=4, I have to do a little bit more. I have to add this piece that comes from the scalars. Okay? And I have to do that because that's how the multiply works. And the simplest way to think of this is, if I write this in 10 dimensions and then I reduce, you will definitely have this field, right? So this is, you probably can understand. But this is the N=4 Wilson loop. So this is the N=4. And this object is supersymmetric if I take the right contour and I take the right combination of fields. So again, x mu is the path, while I is going to be a square root of the speed, and then there's some vector, there's some unit vector. Because I have 6 scalars, so this is essentially picking a direction in the space of a scalar. Good. So this is the object, and we want to evaluate that object. Good. So let's evaluate it. Now all we need is just field theory. Okay. So let's see how we evaluate this. So now again, I wrote the whole thing in all detail once, but now I'm going to be a little bit more schematic. So I want to evaluate the expectation value of the Wilson loop, and of course, okay. So the idea would be to essentially, I want to do it in perturbation theory. So in perturbation theory, I assume that there's some coupling. I have been a little fussy with the couplings, but there's a coupling G that is small. And then essentially what I'm going to end up doing is, I'm just going to write it in words. So I'm going to expand the exponential. Expanding the exponential essentially means that I have to deal with objects.
What is J?
What is?
YE.
So YE, so X, so this tells me the path, and Y is just, so I have to also, you see, this connects with A mu. So because it's N=4, I need to put the scalar here too. And so I need something that is not a vector, but it's sort of like a dimension of this vector in space. But it's just the velocity of this path. So, okay. this will become a lot clearer when I go to direct evaluation. So what I want, expanding the exponential means that at the end of the day, I will end up computing correlators of this type. So this is path order, so I'm going to have, let's say, a piece like this, and then I will have many other pieces, I, A, tau, let's say, N. Okay, so the first term, of course, the first term is just 1. The second term will be just one field that will be kind of like topologics if I am expanding. So the first correlator that I have to compute, will be something like, let me write it. Yeah, write it here. Actually, I'm going to, so this is the general case, the general term there, but let's assume that I'm just computing the second term, okay? So this, okay, so I need to tell you what essentially the Green's function for the gauge field and the scalar field are. I'm going to use Feynman gauge just to make things a little simpler. But the answer to this, let me write the answer, and now we are going to discuss a little bit. A and B are indices in UN. Then I have 4 pi squared. Minus x dot 1 dot, and all this divided by x1 minus x2 all squared. Okay, so what is going on? As I said, this is a term that appears. I'm trying to evaluate this perturbatively. Okay, so this is the first sort of non-trivial term. I want to evaluate it. I'm discussing a circular Wilson loop, so that means that the path that I'm taking, I'm going to write it now explicitly. So the path is so let's take a path. So we're working in Euclidean space. So let's take a path that is x mu of tau is given of tau. This is all I need to tell you to be able to start evaluating. Would be sine of tau, cosine of tau, 0, 0. Okay? Now,
what is that on the next to G squared? Is that a delta AB?
Delta AB. Okay. Right, because these are really elements of the group, so I really, to write the propagator, I have to be a little bit more careful. But that's, and again, so I'm in the Feynman gauge, so that's, okay, so I will do the evaluation just because I will do the evaluation very explicitly to basically exercise some of the fears that you might have that this is a very complicated field theory equation. This is very easy, so we will do it right now, and you will see. So I need to essentially, this is essentially kind of like the correlator here that I want to evaluate. So what is the velocity that I discussed? This will be. So it doesn't matter, but I just to stick with my note because otherwise I will make mistakes further down. So this is the same thing, right? So the velocity of this one is 1 because it would be, right, the derivative of cosine because it's derivative of the speed. So that would be minus sine of tau squared plus derivative of sine is cosine of tau squared. This is 1. Okay, so when I see this, tau is because okay, so remember that this is ordered. So my tau, I have this. Make 1 liter. Make 1 liter. Okay. I'll fix it as we go. 1 second. Okay, so then I need to evaluate this. So this is, because you see I have to order this path. So that means that in fact, when I'm expanding my exponential, and this is something I did not do very explicitly, I will have terms that will be, so d tau 1. So this one you have seen in field theory, I expect. So then this will go from 0 to tau 1, and then this will go from 0 to pi, if it goes around like this, right? So this is why I have 1 and 2, because that corresponds to having parameter tau 1, right? And parameter tau 2, etc. So let's evaluate this quantity. And again, evaluation is very simple. I already told you what the path is. So what I need to do, you already know what the velocity is. So let's compute this. This computation will be 1 times 1 in the numerator. So I have 1 minus. Then I need to take the scalar product of 2 vectors like this, right? Good. So, but this scalar product is very easy. So x dot, let's write x dot just because we're going to use it a lot. So this is minus sine, and then this will become cosine. Now this is the speed. Okay. So I need to multiply this with the one with parameter 2. So what I get here would be minus. So allow me to just allow me to. S is sine and C is cosine. Okay, just because that way it's simpler to write. So the product, this product here would be minus sine of tau 1, sine of tau 2, minus cosine of tau 1, cosine of tau 2. Right? It's just a scalar product of this with something like this with a different tau. Right? That's what you get. And in the denominator, what I have is going to be absolute value of cosine of tau 1 minus cosine of tau 2 squared plus sine of tau 1 minus sine of tau 2 squared. That's the difference squared. Now the key thing here is that so I'm going to write one trigonometric identity so that you see that this is all there is. So let's keep in the numerator is like this: sine of tau 1, sine of tau 2 minus cosine of tau 1, cosine of tau 2. And the denominator, what do we get? So this one I'm going to open in 2 steps, in 1 step, so that, so I have cosine square of tau 1 here, and sine square of tau 1 here, that gives me 1. Cosine square of tau 2 here, and sine square of tau 2 here give me another 1. Okay? Then these are the mixed term, right? Minus 2, cosine of tau 1, cosine of tau 2, and here also the mixed term, minus 2, sine of tau 1, sine of tau 2. But you see, now what this gives me at the end is 1/2. And this is really the eureka moment, because what this is telling me is that when I expand my exponential, so I just show you at one other level, but everything that you do further down will be weak contraction of this kind of combination, but they are independent of the path. X did not enter, tau does not enter, everything cancels. So that means that this at the end is just a combinatorial problem. I just have to tell you, you have to be careful of how many contractions you will have. But the problem, and this is the thing. So again, just to finish my point 1, perturbative evaluation, let's write a formula. The Wilson loop, circular Wilson loop in n equals 4 to first order is going to be g squared n divided by 16. Okay, that's that one we did. And we can now have the machinery to go to any order we want. Okay? And the key thing was this, that this correlator or this 2-point function was for this particular path, okay? You have to be the circular, I told you it's especially supersymmetric, but for this path, the answer is independent of the path, and therefore it becomes just a combinatorial problem to find it. So this object, okay, so actually, just to, this I will not give you as a homework, but I give you as a suggested homework for on your way back home or something, okay? So you can, I told you all the ingredients, okay? At the end, it boils down to some combinatorial problem on counting how many weak rotations I will have. And I'm going to write the answer for you. Okay, so g squared n divided by 4 to the n divided by n plus 1 factorial n factorial, okay? So this, people, in fact, people like, so let me now give you also references a little bit. So Drucker, Gross worked on this, and then there was also, or maybe, okay, Ericsson, Seminov, and Zarembo. So this was in the year 2000. Very quickly after ADS-CFT, it was understood, okay, we need to look at Wilson loops. There's one Wilson loop that is special, it's this supersymmetric Wilson loop, and let's evaluate it. So they started evaluating this and realized that this is indeed the case. And then right there, they make a conjecture. Okay? And the conjecture is very natural for, okay, the conjecture is very natural, given that this became a counting problem, so the conjecture was that the whole thing was given by a matrix model. Because of course people in the 90s and in the early 80s developed technology to compute matrix model, and they knew exactly that this counting problem is the counting problem of a matrix, Gaussian matrix model. Okay, so that was immediately. So this is this guy's conjecture that the whole Wilson loop is given by a matrix model. Gaussian matrix model. I'll go to that matrix model after I tell you one more thing. Yes?
N equal to 4 played a role in this discussion?
N equal to 4, it did, in the sense that this is the object that is the Wilson loop in N equal 4. For N equal 2, you will see that for N equal 2, this doesn't work. You'll see. This story is very beautiful, but we'll see. N equal 4 plays some, it's not explicit, but you will see that it comes. Has to do with the supersymmetry. Okay, so what we have discussed is strictly field theory. Okay, but of course, ADS-CFT motivated people to look into this object. Okay, it's an N equal 4 object. The technology is very simple, as you can see, and then okay, so this is the conjecture. So I don't want to go into a lot of details, but the diagrams that I'm counting here are very specific type of diagrams. So they are rainbow diagrams. I don't allow crossing of lines. I'm looking at planar. So there are some simplifications, okay? But I don't want to go into all details. But that's why this was a conjecture. Otherwise, it would have been just. Otherwise, once you get here, you can say, I know this counting problem is a matrix model. You don't need to conjecture it. This conjecture is here because you're only counting a set of diagrams. There are other diagrams that you're not counting. You're assuming that they will be something. Okay, that's the conjectural part. Yes?
Why do we have a path or a circle in the temporal loop?
So this is, so a Wilson loop, a general Wilson loop is given by, you have to give me the path. Remember, you take a quark, a heavy object, you move it around. You move it as you want. What is beautiful here is that if you move it exactly in a circle, this is going to be a supersymmetric configuration.
This circle is, I thought that the circles or the paths are defined in the spatial.
This is field theory. There's only space. This is field theory. I have not said anything about ADS, extra dimension. This is just something that you can study in quantum field theory 101. So after you know how to do correlated, you can do this problem.
Are you bringing down the vertices from the interactions? From the action?
Here?
Yeah, evaluating the correlation functions. This is a free propagator, right?
Yes.
But no vertices are allowed, no interactions from the action. Cubic interactions.
Okay, good. So no, these are just doing perturbatively, and I'm just looking at the vertices. That's what I was saying, that I'm looking at essentially a rainbow stuff. I don't allow.
So in Scranum you get those.
Exactly. Yeah. Exactly. So now there's, as I said, my goal today is this is my last chance. So I'm going to throw everything I can. So I told you I want to teach you also techniques. I want at least point to you that there are techniques that are very powerful, so you can go and study them. So this was a very interesting calculation. As you can see from the question, there's some subtleties, but this was a conjecture in 2000. Now this was proven very rigorously in 2007, at the end of 2007 by Pestun. And this is another thing that definitely you need to be aware about. You need to, as an educated person in string theory, you need to know this story, so I will tell it to you very quickly. So Pestun, 2007. Okay, so it took a while, and this was very puzzling. People were very interested in this conjecture, but here is the story. So, and this is very general, okay, and there's actually a lot of activity in string theory and in high energy about motivated by this work, because you will see how powerful this is. So suppose you have some path integral, okay? Okay, the key thing here is that I have to be in the supersymmetric setup. If there's no supersymmetry, I cannot do much. But I'm interested in understanding that supersymmetric object. So suppose I have some supersymmetric theory defined like this, some path integral. So supersymmetric theory means that there's some supersymmetric charge, right? Supersymmetric operator, and my action is invariant on the task. Okay? Then I'm going to cook up an object. Okay, to say this carefully, it would take me a while because I have to talk about, say, my positive definite. I have to be very careful, and I don't want to be super careful right now. I want to give you the rough idea of how this works and how powerful it is. But again, I'll be happy to discuss this personally because it's a subtle. It's subtle. So suppose I have some Q. So I have some. I have some V such that QV is positive or positive definite. Okay, then I want to consider the following problem. Instead of my path integral original, I'm going to deform it. I'm going to deform it by some parameter t. And now my problem becomes d phi exponential minus s of phi minus t minus t qv. So that's the deformation I want to do to my theorem. You see, now in principle, I went to a different theory with some different action. It depends on this parameter t. But here's the miracle. So if I compute the derivative of this with respect to t, okay? If I do that computation, so what is going to happen? Okay, so the answer is that this is 0. But now let's see more or less. Let's see what the ingredients that you need. Good. So when I differentiate this with respect to t, what happens is that this goes down, right? So I have, so let me do one step. So d zt dt is essentially going to be d phi. So I'm going to be, again, this is not super kosher, but it's just to give you an idea, okay? This comes here. And now I'm going to use, I can rewrite this as, d phi. I can use, so remember that Q acting on S is 0. Q is on supersymmetry, so I can make a choice of V so that Q squared on V is 0. Okay, so then what happens is that I can write this roughly as a whole, this kind of derivative that will essentially be like a boundary term, and that's why if I am in the right manifold, so there are many subtleties here, I'm sorry. So if I'm in the right manifold that doesn't, let's say something that doesn't have boundaries, this is 0. Now what is it that we have won? We have won a lottery essentially. This is really equivalent to winning the lottery. Why? Because now you prove that this thing is independent of t. You can evaluate it for t equals 0, which is what you want, or you can evaluate it for t infinite. What is the advantage of doing t? What happens when t goes to infinity? So t here is like 1 over Planck's constant. Okay, it's h bar, right? So taking t to infinity is essentially making this theory classical. And in a classical theory, I exactly know what to do. I find the solution of the equation of motions, and I evaluate, and that's my path integral. You see, your path integral, very complicated, depending on many variables, etc., becomes now a classical problem, okay? So at t equals infinity, what I need to do is to evaluate the solutions of my classical action. So this is sometimes called localization locus. There's a lot of machinery behind this. I just want to tell you, there's some very important technique out there, and you need to learn it, okay? Because it's incredibly powerful. So that turns this problem into a problem of finding this. And of course, there's one more subtlety. I have to consider one loop correction, because at one loop level, this t cancel with the, remember, t is like h bar, so at that level they cancel. So I have to also compute one loop corrections. But that's it. So I'm going to write for you the answer. The answer of my z of t will be phi 0. Now, instead of integrating a path integral over all possible phi, I only have to consider the phi's that make this true. And that, in the case that we are interested for this n equals 4 Wilson loop, it turns out that phi was a field, and this phi 0 is just a matrix. That's how it becomes a matrix integral. But let me write it for you. So then is minus evaluated on this phi 0, and then I will have some one loop correction. Also at phi 0. And this is really the powerful, so this is really the power. A completely complicated path integral becomes, in this particular case, a matrix integral. So so is this clear? Again, I don't expect that every step is clear, but the logic of what's going on is clear. If your theory, you see the heavy lifting here is being done by supersymmetry. Supersymmetry is the one that allows me to make that path integral a boundary integral at the end. So the action has to be invariant. I have to be able to find such object, and that has to do, again, that would be supersymmetry is all over the place here. Okay, but in this case, I can do it. Now I want to make one remark, because okay, at this point, what I was saying seems very abstract. But suppose that my S, you see, I can add to S. To S, I could add, so remark. So I can add to S any supersymmetric object. And in particular, let me write it like this. I can write my Wilson loop, because you see, if I want to compute the expectation value of the Wilson loop, I just have to insert it in the path integral, right? It's a little bit like adding it to the action. But still, you see, my argument works, because if the Wilson loop is supersymmetric, I just have to put here, I run my argument again, and I can evaluate now the expectation value of the Wilson loop. Okay? So that is what Peston did in 2007. And the answer is, so I'm skipping many steps, but the answer is that precisely the n equals 4, that the answer is that this coincides precisely with the matrix model that Gross and people conjecture. So that is the proof. Okay? But you see, there is a lot of, as I said, there are many great things about this. So one important thing is that it applies to any supersymmetric operator, but also one great thing is that there were no Feynman diagrams here. There was no summing over anything. It was just this very beautiful mathematical statement. So that's why. So when I was a student, I was always scared of localization, because I thought this is some monster that lives in topological field theories. This is probably something I never have to learn. But you see, it is a powerful thing, and it has this very concrete application. So I really advise you to become familiar with this. It's like part of your education. It's a very powerful tool, and it answered this question. So for 7 years, this was a conjecture, and now it's been proved.
Sorry,
yes?
Where localization enters the discussion?
Because localization means you had a very complicated path integral over all possible configurations, over all possible functions, and at the end it localized to integration over some matrix.
And what's the physical mean that path integral is independent of
The physical
the physical interpretation?
So I mean, good. So I don't really have a very physical interpretation. I have, I would say, theoretical, physical, mathematical interpretation. This is kind of, you have to. Okay, I don't know. You have. I mean, we can talk about what is your approach. But if you're mathematically minded, then you think of this as some kind of deformation problems. There's some space that you can deform, doesn't cost you anything, and that's really what's going on here.
It's a useful tool.
But physically, okay, so physically I view this as it is possible. I mean, there's a lot of supersymmetry in the problem. One could have just done what Gross and friends did at the beginning, try to compute. But then you will always have some holes in your computation. And this is yes.
Just one. Trying to understand this identity. It just looks very odd to me that, for example, if you take especially you have the Pando-Zayas statements, and you say QB is positive, while you're integrating over a measure, which in principle is also positive, if you take t equals 0, how could you possibly get 0 out of integrating something which is strictly positive?
Okay, no. This last step says that this becomes a boundary term. If I'm in a suitable manifold, then this would be 0.
But for this to become a boundary term, then Q has to be some kind of operator.
Q is a supersymmetry operator. Q on some fermions give you, or in some fields give you something akin to differentiating if you want.
So if Q is an operator, how is it possible that Q acting on these positive? Is it positive as a number or positive as a number?
Okay, no. Okay, I don't really want to go into a lot of detail. I can write for you. I thought I would do it, but I think it would take me a little bit. I can do this very explicitly for you in the context of n equal 4. And V, so what does V have to do? I want to add something positive to the action, like QV has to be positive. So let me take V to be Q acting on these fermions multiplied by a fermion like this. So when I add with Q, this will be positive definitely. So this is a choice of Q. This is the preferred choice of V, sorry. I mean, this, I can go into more details on how this exactly works, but fine.
Maybe we can set it later.
Okay, so, good. So now we know that this matrix model was a very interesting conjecture that was proved. Okay, so I want to also, okay, I guess probably next time I will demand that I get extra lectures because I wanted to do many things. So the other thing that I wanted to teach you how to compute it, because I told you it's a matrix integral, but okay, but I guess that this is okay. So this is going to be a little difficult, but let's see how much I can convey. Okay, so matrix. So we're now here. So matrix model. So this is again, this was developed. Many people, in particular the French school, developed this in the 80s, and this is a well-established. Of course, Dyson and many people worked on this before. But essentially, what you want to do is integrate over matrices, and then you have. In this case, I'm just going to talk directly about the case that I'm interested. Some matrix square, right? The Gaussian matrix model. So this would be lambda. Okay, so there is technology to solve this exactly, to solve this kind of problems. And I want to give you some flavor. Okay, so the last part I told you, the last part of the talk with Fliponet, this is also should be considered in that category. Again, it's a pretty area I had. Ricardo, so an undergraduate student can understand this in a few weeks. Okay, so this is not a super complicated area, but it's very useful. So if you want to compute this, the key thing is to find the right basis, like in many problems, right? And the right basis turn out to be the eigenvalues of this matrix. So this is diagonalizable, and then this problem becomes a problem of integrating over eigenvalues. So I'm going to write it like this. So this becomes a problem of integrating over all the eigenvalues of this matrix, and then this diagonalized, so it essentially becomes sum of the eigenvalues, in this case square. But there's a determinant. That's the main non-trivial part. There's a Jacobian that I have to respect that Jacobian. So he's there because I went from this basis Mij, if you wish, to this basis, and then this is called the Van der Monde determinant, and in this case it's essentially okay. So I will not write it explicitly. It doesn't matter much. Okay, there's some determinant here, but that's my problem now. I just need to integrate over some numbers. And this is of course the partition function. To evaluate the Wilson loop, I need to introduce the Wilson loop. So let's good. So let's the Wilson loop in this case. It became essentially, I told you, the whole path integral went to a matrix, which I will also call M. And essentially what I'm computing is going to be expectation value of e to the m in this case. Okay, that's going to be that's what the Wilson loop is going to be. So I have to now, let me be a little bit, so now I have to sum here. Essentially again, I go to the same basis, something like this. Okay. Now the thing is, oh wait, it's a little bit. Now the key problem is that so let me write this expression. So because m brings an eigenvalue, well, it brings all the eigenvalues, but every eigenvalue in this product will be more or less the same. What essentially at the end of the day I'm going to end up. So let me write another expression. Okay, I'll try to lambda. Okay, I will not. It's a little bit complicated. So let me write. The key thing is that I know the answer for this problem exactly. I can tell you a little bit what piece of technology I need to use, but it's not enough to be in this. I have to find some. Okay, let me write the answer. So here's the answer for this Wilson loop. This is the Laguerre polynomial minus lambda over 4n exponential of lambda to the 8n divided by 8n. So this is the exact answer. Okay, and what happened is that there's technology for me to compute this matrix integral exactly. Now the key words here is orthogonal polynomials. That's the technique in matrix model that allows me to do this. And essentially what I need to do is to rewrite this determinant in a form that it will allow me to find polynomials with respect to this new measure that would be orthogonal. And then this calculation simplifies, and this is the answer. Yes?
I don't understand that part because we have the eigenvalues. I just need lambda.
Okay, I'm sorry. This lambda is really the Hopf lambda. So here, I started correctly, but then I messed it up at the end. So the lambda is the Hopf coupling that was here. Okay, here I had G squared. So normally, what you would write is 1 over G squared. This is what I wrote when I was showing to you how the Hopf argument works. But because I want to work in the Hopf limit, instead of this one, I'm going to write lambda n. That's the coupling, and that's the answer. The answer depends on lambda and n. Yes?
When you said that this is the correct answer, it is just in the LASS n?
No. This is exact. Any lambda, any n. It's just, this is the exact thing. But of course, because this is an ADS-CFT lecture and I want to connect with ADS-CFT, I'm going to take the Larsen limit of this object. And the Larsen limit of this object, again, so it uses, so here's the Larsen limit. This is the Bessel function, square root of lambda. divided by square root of lambda. Then O over 1 over n squared. Okay, that's that. Now what we want, this is still, I don't think that everybody dreams in Bessel function, so I will explain it to you what it does. In the limit that I'm interested in, lambda very large, this is the square root of lambda. And now then you feel, okay, I can see I can get that from a string, but this is essentially what happened. Then there are corrections here. And remember, this talk, if I get to the end, is about this thing here. This is what I want to essentially prove. What ADS-CFT does beyond the leading term. But you see, everything in the field theory, I have not used gravity anywhere. This is all field theory. And field theory gives me what I call you at the beginning. This is high precision data, right? Because this is exact. So now my question is, how much of this can I get from holography? Okay, that is my question now. That's my goal. And of course, I have no doubt that holography can do all this. But in the way there, I will learn if I need to fix something in holography, if there's something that I don't know exactly what to do, that I'm doing wrong. This is my test. This is my data, right? This is my experiment, and I'm now going to try to get that from my holography lab.
So you know, in theory, what are the corrections?
This is the answer. This exponential is just I'm expanding in the large lambda limit.
You will compare this with what you obtain from holography.
Exactly.
Could you write it as the correction?
Right, what?
The correction.
Yes. I said my goal today is quantum ADS-CFT. I will compute this. Okay? Good. So now let's go to holography. In holography, I'm going to be a little quick because by now you're experts in Wilson loop, and you have already computed the main one. This is a circular Wilson loop. Of course, you want to also go into the bulk. This is my gravity thing. It's just this number go to string. Let me remind you. So ds squared, I live in ADS 5, so I will write the metric again. But you see, the first Euclidean ADS 5, right? No time, everything is space-like, so I can have extra coordinates here. This is my metric, right? I want to find the surface because, okay, I know what it is, but it's good to get an equation. And this is the part that we already did for the quad Wilson loop. Right? That was exercise number 2 in ADS-CFT. So now we want to do it for this Wilson loop, but the technology is the same. Now what I need to find, so this is in polar coordinate, this is the R, this is phi, it's around this, right? And Z goes down, okay? But what I need to find is the surface. So I need to find how Z depends on R. But then I have a very simple problem. It's I have to take my Navier to action, which is L squared divided by 2 pi alpha prime. And so let me write the induced metric here, just so that you are completely comfortable. So the induced metric on the worksheet is going to be, so I told you that C depends on R, so essentially I'm going to have L squared divided by C squared, R squared d phi squared. Okay, now to wake whoever is sleeping, what's the next thing that I need to write? What's the next term? I know I wrote it very low, so some of the people cannot see, but so I'm writing this metric in this worksheet, and this is my bulk metric, if you wish. So what are the next terms that I need to write?
Z squared.
Sorry?
Something with Z prime.
Something with Z prime. That's good enough. So dr squared 1 plus Z prime squared. That's the. And now the number go to is the determinant of this thing. And so it's going to be integral dr, d phi. These are my worksheet coordinates. R, right? Because I have this R over C squared, the square root of 1 my C prime squared. And at this point, this is seriously, at this point I can give this to a high school student because this is a classical mechanics problem. A problem of minimizing Z, and it's a little bit more complicated, okay? Because now, remember the one that we did before, so phi is, of course, this is symmetric. So let's write 2 pi, and essentially let's cancel this 2 pi with this 2 pi, right? So this is the only problem in this classical mechanical problem is that it is time explicitly dependent on time. So there's no easy integral of motion for me, but this is something that you have to learn in classical mechanics, okay? Nothing more. So this can be solved. So I'm going to write the answer. A squared is the radius of so this radius, this distance is A. So Z wants to be R squared minus R squared. So essentially it's also a circle inside, or kind of a circle inside the ball. That's the solution. And good. So now I have to evaluate it. I found the solution. I have to plot the solution here and compute. And you already know that there will be a divergence, right? And that I have this powerful thing called holographic renormalization that I tell you nothing about, but that will save me, okay? But I can also understand the problem physically, as we did with the quarantine quark. So I can understand the divergence, whether the divergence comes from some extra piece in the problem. Okay, but I can do this calculation. I will not do it in all gory detail. This actually may be a leave as a homework for you, but it's very straightforward. Okay, it's just analysis. And at the end, the answer is going to be, so again, let me highlight the key points. So there's divergence. So that means that I'm going to introduce some regulator epsilon, as I did before. The divergence comes at Z equals 0, right? That we more or less understand. That has to do the volume divergence in gravity, which is connected to UV divergence in field theory. Okay, so let me not say more. The answer is going to be minus the square root of lambda plus the square root of lambda A divided by epsilon. Okay? This e to the minus s matches precisely this. So at this point, and this of course people did very early on in ADS-CFT, bingo, right? So any questions so far? So now, now I want to go to the dot dot dot. So how do I do that in holography? Well, so I'm going to use semi-classical physics. So, and this is again very similar to the paradigm that I mentioned in localization in the last part. So you compute the classical piece. This is the classical piece. And now I'm going to expand around this equation. I have to expand and include the fluctuations. So now we do fluctuations. Okay? And then, of course, I integrate those fluctuations. That's what semi-classical analysis is about. So, good. So again, what I need to do is to take, let's say I have x, I have to take x. So again, really think of this as now allowing, this was my surface, my classical surface, and now I'm going to allow some wiggles, right? So now my surface can be like this. It's a quantum surface. It's sort of bubbling, moving around, and I need to interpret that. That's going to be corrections to the leading term, right? The one-loop determinant there. Okay, so I'm going to do something like this, right? This is the fluctuations, and then I integrate over the fluctuations.
That is in the bending.
Sorry?
This is in the bending on the worksheet.
Isn't?
The bending.
Embedding.
Bending.
Sorry.
Embedding.
Embedding? What embedding?
Yes. What does she X mean?
Yes, this is a okay. So this is good. Thank you. So here what I did was I had all the coordinates of, let's say, ADS5, R, phi, Z, X, I. I need to tell you how they, what do they do to become this minimal surface. And what I said is that, okay, I'm looking at a string, so this is going to be like tau sigma. Okay, so here's the question that you're asking. And what I decided was that, okay, R and sigma will be, R and phi will be tau and sigma. Z will depend on sigma. And the other ones are going to be constant. That was the embedding. Now I need to allow all these things to fluctuate. Good, thanks. Which is collectively denoted like this. And now, and of course, what I need to do, essentially, I'm going to take Nambu-Goto and expand it. I already told you, we already had this problem of expanding Nambu-Goto when we were deriving the leading term of Dirac-Bonnefeld. Okay? So again, it would be the same problem. So maybe let me remind you. The tau, the sigma, and I have of G induced. Okay? So now I have to go back and compute G induced that allows these things, these fluctuations, and I will write everything to second order. I also gave you a formula for expanding these things to second order. Remember, first order is going to be 0. Why? Because it's the saddle point. It solves the equation of motion, which is essentially the variation, the linear variation. So I only will get the second order. So at the end, let me actually write the answer. I'm going to write it. I'm going to write the full thing. Okay. D squared sigma, symmetric. So at the end, I'm going to have. Okay. So let me. Okay. So. And then there's another piece that is going to be some matrix XB. Okay. Okay, so let's step back. So what we need to do, I already told you. I just take this action and expand to quadratic term. And I call the fluctuations here. So now, okay, so let's separate the two things. So what I need to do is expand this to second order. And I can just plot my solutions and do it. But this is a very geometric problem that people solve in the 1800, okay? So there's an organized way of doing this. Instead of just naively putting everything, whatever in the metric you saw X, substitute, there's a much powerful way of doing it, in which you try to define some field binds that I call A, and they come from the field bind of the whole solution. So instead of looking at this delta X mu, you look at the field bind, and that really is an object that then gives you a geometric interpretation. So this will come from the Riemann tensor, for example. Okay, and there's some gauge fields here that appear very naturally, as they have to do with some. Okay, so they have to do with you're expanding a surface, and there might be intrinsic curvature of that surface into some other space. Okay, again. Conceptually, what we need to do is very clear. I'm just using a very powerful hammer to do it, because that way I know I don't make mistakes. Somebody solved this problem for me, told me your answer. So again, so let me write this formula to convince you a little bit that what I have done here is a little bit is very geometrical. This is E, D, J, this is the work volumetric, and then this is the Riemann tensor, A, B, C, D. Okay. So that if you did background field theory, the background field method in quantum field theory, that's exactly what I'm doing here. I'm finding, because the space is curved, right? This is the old problem that you have seen. If you have done nonlinear sigma model, this is an old problem that happens there too. So the coordinates are not well-defined objects; they are not vectors. Okay, so you have to go to some object that is vectorial, and then when you expand, you will only get tensorial objects, and that's what I have done here. But the key thing is that I know all the fluctuations, and I can double check, triple check, all that. And this is the form of the general answer. But what I'm interested is then I integrate over these fluctuations, right? This is a Gaussian integration, and that will give me my one loop correction. So let me write it like this. I will write something, and then we will interpret this. Okay? Together. Okay, good. So now we're ready for the interpretation. This is, again, I write quadratic fluctuations, I integrate it, give me determinants. So what happens here, so this a determinant that comes from the fermionic variation. I didn't write the fermions here, but of course I can use some Green-Schwarz formulation where I also variate the fermions of this theory, and this is the Lagrange, the determinant that they give me. This is the Laplacian because I use some identity, and this is the two-dimensional curvature of my worksheet. The worksheet, in fact, if you work out this a little bit more, you will see that the worksheet is an ADS2 that has constant curvature. So this is some number, but this way you know the answer. And now I have to, you see I have two different bosonic modes. The determinant of boson goes to the denominator, right? And I have two kinds of modes. I had three modes, right, that were sort of massive. And what they correspond, I told you the worksheet is ADS2. And I embedded this into ADS5. So I need essentially three degrees of freedom, and this costs energy to move ADS2 inside ADS5. And that energy exactly is this. Okay, so that's the determinant that comes from this fluctuation, how ADS2 fluctuates in ADS5. Then I have fluctuations on S5. And these are completely massless, so fluctuating there didn't cost any energy. It's this. Okay? So that's my fluctuation, that's my one loop. And this would be my one loop correction to the object, which is this Nambu-Godu, right? String. Now, so now I would have loved to teach you how to compute this determinant. This is an interesting story. Maybe in this Monet part, I'll show you how to do it. But roughly, this can be computed. These have been computed by many people, of course. And I'm going to just write the answer. So the answer is, so let me write gamma 1, is the effective function for this problem, is essentially a half log of 2 pi. Okay? So that's what this problem gives me. So now let's compare. Let's compare. I remember I had the field theory. I'm doing my theoretical experiment. So let me remind you. So comparing. So the field theory was 2 over square root of lambda I1 square root of lambda. And when I expanded this, it became, okay, let me write like this, log of, became square root of lambda minus 3/4 log of lambda plus a half log of 2 over pi. And then plus, there are things that I can write down, but they would be now ordered 1 over square root of lambda. Now the gravity side, essentially, so let's write like this, minus s is going to be a square root of lambda. I missed this term completely. And then here I got something plus a half log of 2 pi. Okay? So, good. So now let's see what's going on. So we failed, right? We did not get what the field theory told me the answer is. So we failed. Okay? This is very important. These people computing around 2000. Also, I mean, once you have the classical thing, computing the one loop correction is there. So for 15 years, this is the status. Okay? And people have recomputed, and still this is the status. So let's see what's going on. There, this term, this minus 3/4 lambda to the. So this term is, if you think about this term, well, if you think a little bit more, this what happens is essentially that you had the answer from field theory of this essentially at some point was the square root of lambda here, and then I have 1 over lambda to 3/4 here. So because it came like this, you can think of this as this might have come in my calculation by some sort of zero modes, some sort of, and this indeed, I'm trying to do string theory. So what I wrote here misses that part, misses the part that I probably started with. I started to do in a string theory in flat space. We know exactly that there's some extra zero modes depending on what you do in your worksheet and that they contribute. Okay, so this part we're missing here. So this tells me if you're serious about ADS-CFT, try to learn this part because you're missing it in most of your calculations. But that's okay. Then there's this part. And this part, okay, at this level, there's a discrepancy, but it's numerical. Okay, so this I can probably say, oh, maybe if I didn't know how to handle this zero mode, there might be some constant shift that affected this part. But you see, this is telling you that that we need to improve our machinery for computing one-loop corrections in ADS-CFT, and this is a very important, very typical object. Okay, so this is a problem that, of course, I'm working. Many people are working, but you should consider this problem because it's very interesting. And what I want to, I think, any question about this? I guess in a school it's probably not very kosher to finish with a puzzle, but I think that it's good. It's good that you know that there are some things that are not exactly in place, and that there's things that we need to learn. What we really need to learn, and this is something that probably you have heard, is that the problem is that we don't know how to do honest string theory in curved background with Ramon fluxes. So I'm using semi-classical expansion here, and that doesn't give me the answer I know is right. So I need to improve that technology. That's sort of like the message of this exercise. But now I want to give you, if my computer allows me, I want to give you a more complete list of these kind of problems. And there's hope, of course, there's hope. Because, so let me, while I get this to work, let me tell you how this can be solved.
What was the error here?
There's no error. This computation, as I said, I have done it, Gross did it, Sailing did it, many people have done it. This is the answer. There's not an error. The error is in the assumption. There are elements that we are missing, that we know we're missing. We don't have a really good treatment of zero modes in this string expansion. Okay, and that's really the key thing.
At the level of gravity approach.
At the level of the gravity approach. So it's telling me that if you want to compare with the string stuff, you need to, that technology of the string needs to be upgraded. Let me see if I can.
Estaba pensando de qué ves como parámetro de formación. Okay, so I'm going to tell you a little bit about a few challenges in ADS-CFT. They are all in the same class of problems.
but it's a little bit more general. Again, my collaborators here, Alberto Faraggi, who was my former PhD student, is now in Chile. Wolfgang Mook from Naples. Here's an undergraduate student from China. It's now, I think, a perimeter. A colleague of mine from Michigan. And I don't like to be chauvinistic, but this is I'm very proud that this is a truly Latin American collaboration. And I will tell you what the goal is. The goal is really to try to solve that puzzle. So because I don't have a lot of time, let me give you the punchline now. How can we solve that puzzle? The problem we know, the problem comes from some kind of zero modes in the string perturbation theory. But those depend only on the topology of the worldsheet. So I need to find another Wilson loop configuration with the same topology and do the same computation. And when I find the difference, then I should be fine. So that's really what we are doing in this collaboration with Guillermo Silva from Argentina and Diego Trancanelli from Brazil, and then Alberto who's in Chile. So this is really the only way out here. Or once you develop all the technology you need to do string perturbation theory in ADS5 process 5, or you find another configuration, another Wilson loop that has the same worldsheet topology, then therefore it will have everything in that sector will be exactly the same. You compute your one loop correction and then you compare, you subtract. So that's the project, the last project, but I will tell you a little bit about the status of, so there are many other Wilson loops. I told you about the simplest one, which is the one in the fundamental representation. So you can construct a Wilson loop in the K-symmetric representation or in the K-antisymmetric representation. The gravity object is no longer a string. Now it is going to be a D3 brane or a D5 brane. Okay? And these objects I study, and people have studied. So, skip here. This one I already told you. This is a good sort of the same. Here's the localization argument. Again, the action localizes on this piece of the n equal 4 on a sphere. Okay, and that is the Gaussian matrix model. Here's the answer that I mentioned to you. Here's the function. I didn't even write here the minus 3/4 log of lambda, but this is what you already saw. And this is the determinant that I evaluated. This is the puzzle for the fundamental. Okay, so now this is the matrix model technology that I mentioned. So to go beyond the fundamental, I need to develop an extra technology to compute antisymmetric and symmetric, but this is just technology. The key thing is that there's one big part of matrix model is that you can always do large n. Assume that you have, if n is very large, you have many eigenvalues. And then instead of thinking of individual eigenvalues, you think of a distribution of eigenvalues. And this is the Wigner distribution of eigenvalues. And then your problem is some sort of integration along this line. You have to be careful, but as I said, nothing more than analysis. There might be some branch cut that you need to be careful, but you can compute. So this is, for example, field theoretic computation of the one loop correction for the symmetric representation. Okay? So the calculation, instead of using exact polynomials, which I don't know how to handle when I have this complicated representation, I use large n. But this is another technique. But again, it makes all the eigenvalues continuous. This is the leading piece, and this is the subleading piece. Okay? In the large n. This is for the symmetric representation. Now, for the antisymmetric representation in field theory, I can also do it. And one beautiful thing about this higher symmetric, or about this higher representation computation is that I now have an extra parameter, which I did not mention before, but I have this extra parameter kappa in the case of the antisymmetric, or k, or theta k because you see, I'm talking about its representation theories. K-symmetric, they need k boxes, right, in my Young tableau, and this is precisely that parameter kappa. And in the antisymmetric, I also need to have a number of boxes. And so that becomes, I like this kind of problem because I have an extra knob, right? So now I can try to compare with the gravity whether they agree even as a function of k, not just as a number. To match a number is tough, but to match a function is easier in this sense, paradoxically. Okay? So good. So you see, the key thing is that I can do this matrix calculation. I can do. In fact, I had a student from Mexico worked with me in ICDP this summer, and he reproduced many of these computations. So you can study this and you can do it. It's not a okay. So this is a subtle argument. I will avoid it. So let's look at the holographic description for the symmetric representation. That's a D3 brane. Here's the action for the D3 brane that you know and love. It has k units of flux. So sometimes people call this a string that dissolves in the work volume of the brane. All that language essentially means that you have k units of flux. ADS5 process 5. Here's again ADS5. This is the coordinate system that you might not have seen, but it's also the same. And here's the classical solution. U wants to be UK, some constant value, and that value is given essentially by the flux. And the work volume of this D3 brane is ADS2 process 2. That's the full thing. So now my quantum problem will be, let me skip the representation theory here, but my quantum problem will be fluctuations. Okay, here I also know I want to mention, again, this is just, as I said, very, very, this is, I don't want to be, it's very just to give you an idea of what can be done. So there's the Fermionic part that was worked by this guy. The key thing is that now I have my classical solution, and here's the action for the fluctuations. So I have 6 massless scalar, because you see I have ADS2 process 2 embedded, if you wish, on ADS5 process 5. So I have 6 scalars. I still have the fluctuation of the gauge field. Now, interesting, and in fact, I have to admit, I did not notice this the first time I did this calculation. The fermions give you 4 massless wild fermion. So this is the n equal 4 vector multiplet. But it lives on ADS2 process 2. So it's not the one that we have discussed all the time, but these are the fluctuations of a D3 brane. And then I have some technology, this is a representation. So here's, let me discuss this. It will take me a couple of minutes. We already did it in the case of the string, but I want to again emphasize so what we want to compute in all this problem is the one loop correction. In the D-brane fiction, the h bar of the D-brane after everything cancels is essentially n, 1 over n. You multiply the tension of the D-brane by the volume ADS2 crosses 2 that you need to factor out. There's some L to the 4th. At the end, you get n. So this is so in all these problems, this is the kind of thing that you want to compute. This path integral, right? Okay, where again, this is something that I mentioned to you very briefly, but now you can see it. So some kind of reinforcement. So these some sort of operator, and at the end, when I do my path integral, what I end up computing is the determinant of this operator. So this is bosonic, so of course it goes into the denominator. So now, what I did not say before, but it's very useful for you to be aware that these things are there and try to learn about them, because this is a technique that will show up whenever you want to compute determinant or one loop correction. You will have to learn. You will have to use something. So this zeta function regularization is a very typical thing. So if I have eigenvalues of an operator, so the determinant of an operator we approximate by the product of all its eigenvalues. But that usually is a divergent sum or a divergent product. So what we use zeta function to turn it into something regularized. And essentially this is the expression. Okay, I can go into some detail about this, but again, using zeta function regularization, we can compute, there's heat kernel, this is another part. Well, here's the answer. After that, because I know the modes, etc., and I know how they contribute, I can compute the answer for the Wilson, for the Wilson loop in the symmetric representation. Here's the answer. And now, I can do the same for the antisymmetric. I will spare you. Well, here's the comparison. So this is what happened. This was my gravity computation, and this is my field theory computation. Nicely, the function is the same, but there's a sign problem here. And again, believe me, the first time you do this, you say, oh, obviously I made a mistake. So you go back and you check, and you still get the same number. And then you start asking your friends, hey, have you done this calculation and getting this number? But everybody in the community agreed that this is happening. There's this there's this discrepancy. But you see, it's a little bit of progress. So now we understand that this where the expression can come from. Now, but unfortunately, and you see, this is why at the end I end up focusing on the Wilson loop. At the end, for the D3 brane, it's much more complicated to try to understand what is it that you're mixing in your quantum computation. Because in the string, I already know string perturbation theory enough. I know about the conformal goals. I know where is it that I'm being too light. But perturbation theory for a brane, for a D3 brane at this level is really not even developed. So it's not something that I can now go back and say, ah, yes, I missed these goals. I don't know. Okay, so that's why I did not give you this as a main example. So there are other problems in this calculation, but at least the naive corrections are matching. So for the D5 brane, again, blue is always field theory, matrix model, nothing else. And red is holography. Holography has the same functional dependence, but again, there's a factor of 3 here that doesn't quite match. But again, here the story is more complicated. So, but what I want to end up in the last 5 minutes is to just advertise this Latin American collaboration that we're trying to solve, at least for the string, answer the problem. So what I need to do, as I said, I need a string that has the same worksheet topology, and therefore it will have the same contribution from goals and from all that, and that is the quarter BPS Wilson loop. The quarter BPS Wilson loop is defined, this object you already know, and this is the contour that you have to take. It's again circular in this part, but in this space, it's essentially like a cap. Okay, so it depends on this extra parameter. But it can be also computed, it's supersymmetric. So you can run the same Peston-like argument from localization and compute it. And here's the Peston-like argument answer after you do, of course, your matrix model calculation. So I know the answer, okay? And holographically, this is the object. Holographically, it's going to be a string. So this, let me skip this part. But holographically, here's the object. It's a string. So if I take this sigma 0 is this extra parameter that breaks half of the supersymmetry, essentially. If I take sigma 0 to infinity, this is indeed ADS2. And I'm back to the problem that I solved for you today. The BPS string in ADS5 process 5. But in general, I have something that is slightly more complicated. This is the embedding. So you see, it does something also in the 5-dimensional part of the solution of ADS5 process 5. Now, this is the classical solution. Here's the spectrum. We have already computed all the fluctuations. So we have, this is kind of similar to the case of the supersymmetric case. But you see, before we have, everything was massless. All the 5 modes were massless. Now they are no longer massless. They have this sort of massive story to it. So I had, if you remember my determinant, I had 3 modes with mass 2, mass square equal 2, 5 massless modes. So now I have 3 modes that have mass square equal 2, 2 massive modes with this kind of mass, and they are gauged, and then 3 more modes that have some other complication. Of course, in the limit, when I take the sigma 0 to 0, I go back to where I am. So this is the perfect setup to try to tackle this question. Again, unfortunately, we are not done yet. There's some problem computing the determinant. So now, because this is not such a symmetric configuration, we need to use another technique, which is called the Fan-Jaglom. It's kind of like, see the function? The problem that we have, I can tell you, I didn't write it here. Okay, this is too much. The problem that we have is that it's the fermionic sector. The fermionic sector is very complicated. So here, all the determinants we can compute. And we start seeing that this seems to want to work, but to finish, we need to clean the fermions, and that's really the part where we have been struggling for a while. But the key that I want to emphasize is that using ADS-CFT, and in particular this kind of problems, tell us that there's some technology that we're missing, and then we can try to find some place where we can at least factor out our ignorance and get connection and connect with these very beautiful localization results that are completely silent. Okay, I think I'll stop here.
why it's necessary to go beyond the fundamental representation, to include symmetric and antisymmetric from the physical point of view?
Okay, no, from the physical point of view, there's no, so it's just a question of this, it's just because they exist, so I can try to tackle them. As I said, I can compute them in field theory. It's not as nice as the computation in the fundamental, where I have just orthogonal polynomial. I have my answer for any n and any lambda. In these cases, you don't have as much power, but you can have, in the Larsen limit, you can have the answer for any lambda, which is nice, and any k, because you have an extra parameter. My main motivation to pursue this was because they have an extra, it's like I have an extra dial. I have an extra parameter that I might try to see if it works. But there's,
These representations are there, and in principle you have to include.
yes, absolutely.
Okay, absolutely. Another question? Yes.
Why is it so difficult to deal with the non-abelian DI action?
So I don't know exactly, but I mean, okay, so there's one. Okay. My answer is going to be a little bit anecdotal, but so I know one of the person who spent a lot of time trying to construct the non-abelian DBI, Arkady Tsayevin, and I know him, and I know it's like he was my mentor in Russia. So if he could, I mean, it's a very difficult problem, technical to construct, and I think that what happened is that it's hard to really solve the problem. So you have different approaches. You can compute a string amplitudes and try to get the effective function from a string amplitudes. Or you can, I mean, there are different things you can do. They're all very hard. And unfortunately, yeah, this is, I think it's technical. Conceptually, we more or less know what to expect, but technically, I think it's just a hard problem.
But if you have an action for the non-abelian DI, you could try to compute this Wilson. Or it's possible to consider Wilson loops for this non-abelian DI?
No, okay. The Wilson loop is it begins as an object in field theory. So in field theory, I have a gauge field. I can, in different ways, I can compute its holonomy, or I can compute just this quark moving around. So it's an operator that exists in any theory. So it doesn't mean that its action is connected to the Dirac-Monin flow. In any theory that there's a gauge field, I can construct this. The key thing is that it's gauge invariant, but also non-local. It depends on some path, not on a point.
I have a question, but I don't know if it could be explained in Spanish, please. En la ecuación donde tiene esos dos signos cambiados que dice que es por un factor de -1,
sí.
¿Cuál es el hecho de, digamos, ese término es relevante o cómo cambia la física de lo que está calculando ese cambio de signo?
Ok, ¿prefieres que responda en español o...?
Ya, o sea, mi pregunta es en dos partes. Esa es la primera,
okay.
Sí, y la segunda es, porque en el caso de que eso no afecte mucho, ¿no será que la ecuación de arriba le está faltando, o sea, digamos que sea +5, le está faltando el -5 y al de abajo el -5 le está faltando el +5 porque ambos quieren cancelarse? Porque en realidad no, pues quizás está creando una divergencia.
No, yo creo que el problema fundamental es que yo tengo una respuesta exacta y la pregunta es si yo puedo reproducir esa respuesta o no. Es cierto que es el, y la respuesta yo creo que es no, aunque hay diferentes formas de errar, ¿no? Uno puede errar completamente y me da una función que no tiene nada que ver, o esto, digamos, error moderado, que es el signo no coincide. Pero el problema fundamental es, yo tengo la respuesta exacta y yo quiero ver si esta tecnología de holografía me permite acercarme a esa respuesta o no. Y por ahora no, por ahora hay que desarrollar.
Okay, next things. Leopoldo, great.